Hey guys, this is Ryan Nielsen with Group 3, also including Alice Smith and Nate McKay, and this is our Lab 1 presentation. So just a quick review, this class has introduced many of us to Boolean logic. What we're usually used to is our base 10 numbering system, and the algebra that went along with it in elementary school. So what we're used to are the numbers 0 through 9, and this allows for a ton of operations when we're manipulating numbers, such as addition, subtraction, multiplication, division, exponentials, and a whole lot more. Boolean logic, on the other hand, is very stunted, and that's because it is a binary numbering system. This means that there are only two possible outputs. So we like to represent these by using zeros and ones, yes or no, on or off, or as we often see in this class, true or false. Because of these limitations, we only have a few operators that we can use when we move on to Boolean algebra. Essentially, we're limited to addition, or multiplication, and not equal to, not. And even then, these few operators work differently than what we're used to with traditional algebra. The reason for this is because Boolean algebra only has two possible outputs, true or false, whereas our traditional algebra has an infinite possibility of outputs. We can deal with anything from negative infinity to positive infinity. Sometimes they're similar and sometimes they're different. Sometimes our Boolean algebra mirrors our traditional algebra and sometimes it doesn't. So there's no hard and fast rule on when they're the same. We have to take this on a case-by-case basis. So for example, if we look at the first one, x times 0 is equal to 0, that's the same with Boolean algebra, because x and false is going to be false, because AND requires all inputs to be true in order for the output to be true. So it doesn't matter what x is, as long as we have that one false, the output will be false. On the other hand, if you go down a few, we see x plus 1 is equal to 1. In our traditional algebra system, this doesn't work. But in Boolean algebra, it makes perfect sense, because what we're saying is x and 1 is equal to 1, or in other words, x and true is true. And that makes perfect sense, because when we're dealing with ORs, then only one input needs to be true for all of it to be true. So it doesn't matter what x is. The fact is, as long as you have that true in there, the output will be true. So we have that quick review. How do we go from zeros and ones, trues and false, ons and offs? How do we go from that to building circuits like we did in Lab 1? Well, it's all about asking the right questions, and one of the best places to start is truth tables. Quick review for truth tables is, for truth tables, what we do is we put columns for all of our inputs and columns for our outputs. And then we go through our inputs, and systematically, every row, we just change one of the outputs. So for example, in the first row, we can see that all of them are false. Then in the second row, only temp is true. In the third row, only low voltage is true. So we systematically go through and change all of the inputs, so we get every single combination of all the different inputs. Then we look at the outputs. Every time an output is true, what we can do is look at our inputs and pull out a product. So for example, the first time fan is true, it is because we are dealing with chord is not true, voltage is false, and temperature is true. Or another way of saying that is C naught, V naught, and T. That gives us our one product. If you remember the terms sum of products, we now have one product that we will sum up with our other products to give us our full Boolean equation. And down at the bottom, you can see that that's exactly what we did. We have fan is true when C naught, V naught, T, or C, V naught, T, or C, V, T. Sadly, this is just the beginning. As you can see, if we take the entire Boolean equation and try and map it out, it gets pretty messy and complicated. That's not necessarily a bad thing. This can be a great starting off point. The important thing, though, is to realize that you need to do some simplification. And if you're a visual learner, sometimes if you're the type who can actually look at this and see where the redundancies are, you could do some simplification without Boolean logic or algebra manipulation or anything like that, simply by looking at that. And if that's you, that is a great place to start. For other people, there are other ways to simplify. So for example, the way I do it is just with the equations that Brother Nelson gave us. In this example, the alarm is on when C naught V T naught or C naught V T. Using the simplification theorem, we realize that temperature is redundant in this situation and is not needed, so the alarm becomes simplified to C naught V. On the other hand, you could think about this logically. You can see that the alarm is on when the cord is not plugged in, there's low voltage and a low temperature. Or when the cord is not plugged in, there's low voltage and a high temperature. Thinking about this logically, you realize that temperature is a non-factor because the alarm will be on whether or not the temperature is high or low. In which case that gives you the alarm is equal to C naught V. Whichever system works best for you is the best system to use, whichever makes the most sense to you. So a good way to approach all these different problems is to write sums of product equations or product of sum equations, whichever one you feel most confident to deal with, and the ones that you can simplify the easiest is the best way to do it. An important thing is to realize just to take two conditions at a time. Don't try and simplify an entire equation in a single step. You will probably end up, you'll want to take just two conditions at a time and have multiple steps before you go from your original equation down to your simplified equation. The great thing that we have is logism allows us to experiment. So let's say, for example, you weren't quite sure about simplification, and you're wondering if the equation CT plus V naught T is equivalent to CT plus C naught V naught T. Well, the great thing is you can actually put out these circuits. You can put out your inputs, put the gates in, put down the outputs, and hook everything up. And without getting into the nitty-gritty, you look into it and you're going to quickly notice that after playing around with it, that these two are not equivalent. But it's a great way that you can learn while experimenting and learning the system. So we're really lucky that we have that we can figure things out by ourselves as we go along. It's also very important that not just with simplification, we want to make sure that our circuits are readable. Can you read them? Is it easy to see what the inputs are, what the outputs are? Is it easy to see what inputs lead to what outputs? It's not enough to be simplified. You want to be able to look at a circuit and at least get a gist of what this is doing and how does it work. So the easiest way to do it is to start with just the skeleton. So on one side you want to put your inputs, on the opposite side you want to put your outputs, and then within you put all of your gates and inverters. You start plugging things together and you're going to get your answer. So what we have here is the circuits from our group. As you can see, they're all correct, but they all look a little bit different. And that's the important thing, is that just because they look a little bit different, don't automatically assume that you've done something wrong or you've failed your approach because it's a little bit different from other people. For example, my schematic is on the far right. And as you can see, I didn't want to cross any lines. I thought aesthetically it looked a little bit better if I kept the lines from being crossed. But this came with the caveat that two of my inputs ended up becoming gated, so to speak, by the circuit. Now, just to give you a heads up, Brother Nelson didn't dock me any points for that. So Brother Nelson is very much aware that Brother Nelson is very much aware that there are multiple solutions to any given problem. So again, don't think that just because your circuit or your approach to a problem looks different from someone else's that you felt somewhere. There are myriad ways to solve any given individual problem. The important thing in this class is that we learn the concepts, we adapt to what gets thrown at us, and we grow in the process. And here's a picture of our lovely little group, and this will end our presentation.